In this video, I will continue talking about the linearization of a nonlinear system. So in the previous video, I talked about the basic idea how to do the linearization. So the main principle is we don't look at the actual solution. The actual solution for the linear system is still a nonlinear one. However, if we are looking at the deviation from the some control input and the deviation of the actual state from the state calculated based on the input, and also deviation from the actual output and the output based on this control input use of t, the deviations actually satisfy the linearized form if the deviations are pretty small. So that's what it's about. All right. So the basic setup says, okay, if I give some nominal control input, so here I should use nominal, and also have nominal state, and this is nominal output. So the nominal means, hey, for some use of t, and also give some initial values, okay? And we can calculate the corresponding x of t, and once give the x of t and the use of t, and use the nominal x t, nominal ut, we can compute this y tilde nominal one by using this relationship, right? So that means if I give any differential equation, for example, given over here, okay, f sub g, and give nominal input and nominal state, and the nominal initial state, I can compute the nominal state and then compute the nominal output. If we define the difference between the actual state for new control input, okay, and the nominal state, similarly we define the difference between yt and y tilde t and ut and u tilde t. They are related, so this delta means is change of xt, yt, or ut with respect to their nominal values. Once we have that, we can have x delta dot is approximated by at x delta plus bt u delta. Y delta is approximately given by ct times x delta plus dt u delta. So now we talk about what is so the one key question is what is this a sub t, bt, and ct and the use of u dt, okay? So they are given by this. So at is given by partial f x ut over partial x. So this is a matrix. So we'll give an example later on to talk about how we compute the actual value and how this partial is defined. And once we do that, that is evaluated at x is x tilde, u is u tilde, okay? And bt is partial f over partial u, x1 evaluated at s being x tilde and y being u being u tilde. And similarly, ct is partial g over partial x, evaluated at x being x tilde, u being u tilde. And dt is partial g over partial u, evaluated at x being x tilde, y being u being u tilde. So that's how we can linearize system. Basically, we can tell the differences are kind of linearized, and also the the coefficients at, bt, ct, ut, they are determined by two things. One is the function itself, because we have to do a partial derivatives, right? The second one is the nominal state and the nominal control input. So there are two factors will affect this at, bt, ct, and dt. Okay, so here are the basic steps that we're using to linearize nonlinear system. So the first step typically is to compute x tilde, y tilde for given u tilde, x tilde. So normally you will give it this, okay? So in some cases, probably x tilde, y tilde already given, because for the nonlinear system, it may not be easy to figure out the solution. Because if we can figure out all the solution for any possible u tilde, and we can figure out x tilde, y tilde, then we don't have to use the linearized form because we know all the solutions, right? The reason that we do the linearization because we don't know the solution for all the system, but we probably know the solution for some specific u tilde, x tilde 0, and then we try to figure out x tilde, y tilde, and then we can linearize around this, even if we don't know the solution to the nonlinear system for another u, maybe another x 0, which deviates a little bit from this u tilde and x tilde, okay? All right. So once we compute the first step, finish the first step, which is to compute the x tilde, y tilde for given u tilde and x tilde 0, then we can go to the next step. The next step is to compute a, b, c, and d, t, right over here, okay? So last step is we just define these differences. Okay, don't use xt. Don't say xt dot is at xt plus bt and use t and yt is ct xt plus dt use t. You know, this is not correct. This is incorrect because the differences satisfy the linearized form. Okay, which means you define the x delta, y delta, u delta. So you have x delta dot is at x delta plus bt u delta. Y delta is ct x delta plus dt u delta. Okay, so here I'm giving a relatively simple example. Okay, so this one I give a nonlinear system which is y double dot t is plus y t squared is u sub t, and given the initial value is y0 0, y dot 0 0, and x tilde t u tilde t is t squared. Okay, so the question is to find a linearized system about the nominal input u sub t with the initial condition y tilde y0 is 0, y dot 0 is 1. Okay, you sort of can see this. Of course, this is not the same as I mentioned over here, like the original linear system should somehow like this, right? I don't have x over here, so apparently first let's write down in a form that is similar to what we have. X dot is f x unit t and y is gx unit t. Okay, so you can follow the same idea I mentioned in the state space representation. Okay, right, so you have to write it in this form. So okay, let's define x1 as y, x2 as y dot. Of course my x will be just x1 and x2, we put them together. Okay, so do that. So my x will be x1 dot, x dot will be just this guy's dot. It will be the derivative of each individual component, which x1 dot and x2 dot. So x1 dot is y dot, y dot is y dot, right? It's x2. Okay, so x2 over here, and x2 dot is y double dot. So if you look at the y double dot, is this, right? Y double dot, if you pull this one to the right hand side, you get y double dot t is ut minus y squared t. Okay, or you can also do the negative y squared t plus u sub t. Okay, which is equivalent. So which is ut minus, so yt is also given by x1, so I have ut minus x1 t squared. Okay, so I here put the t over here. You can drop the t if you want to. If you don't, that's okay, because I just put it over here to make sure we know it's a partial derivative with respect to x or respect to t, the differences later on. All right, so y, of course, y is just given by x1 because y is just equal to x1, right? Okay, so that's one. So we have here. So this is what we call the f function. So it has two equations, two functions over here. One is x2t. It's pretty simple. The other one is ut minus x1 t squared, and of course y will be just x1. Okay, all right. So this is we can also call this step 0. You just write the system in the x dot is f x ut, y is g x ut. Okay, if it's needed. Now let's move to step 1, which is computed to x tilde and y tilde. When given the initial value, so the u tilde, let's write u tilde t is t, so u tilde t is t squared, and I get x tilde 0. Okay, initial value will be just, as right here is just a y1 0 and a y2 0, right? No, y dot 0, y0 and a y dot 0, and a y dot 0. Okay, y0 is 0, y dot 0 is 1, so this is just 0 1. This is typically is given. Okay, it should be given. So when we need to compute what is x tilde y tilde. So I mentioned here, it is not needed if they are already given. You already given x tilde y tilde, you don't have to compute it. Okay. All right. So let's compute that, right? So this one you cannot do linearization. You just need to use the original nonlinear and try to figure out what is y tilde t. Okay. And also x tilde. I have to figure out x tilde and y tilde. Okay. So let's figure out the initial solution, right? Assuming that y tilde t dot double dot plus y tilde squared is u tilde. That's nominal, because if I look at this one, the nominal solution, you compute this x tilde, y tilde, and u tilde, which means my solution should satisfy my original differential equation, right? Which means it's here. My system should satisfy this original equation. If I put a tilde here, and tilde here, that should be satisfied. Okay, so that's why it should have y tilde t double dot plus y tilde square is equal to y u tilde t. The nominal solution, the nominal input, should drive me to the nominal state as well as the nominal output. That's why it should be the case, right? Of course, the nominal state input is t squared, y tilde 0 is 0, y tilde dot 0 is 1. So we basically want to compute what is my y tilde t, given u tilde t is t squared and y tilde 0 is 0, y tilde dot 0 is 1. Okay, so typically this is very not easy to figure out. So a lot of times, you probably will be given this x tilde y tilde for nonlinear system, unless it's pretty easy to compute. Okay, so here we just use the backward order. I don't show you how to compute it because this is not straightforward to compute the solution. So the solution I give you is y tilde t is the nominal. This is the nominal solution. Okay, the reason I can do the check. Okay, if this is guy, I can compute y tilde t double dot. Y tilde, if y t is t, y tilde t is t, now y tilde dot t is the derivative of this guy with respect to t, right? Okay, because it's a function of t. So the derivative of t with respect to t is 1. Okay, so you take another derivative, which is this guy, so it becomes 0. But derivative of 1 with respect to t is 0. Okay, and y tilde t squared, y tilde t is t, y tilde t squared is t squared. Okay, so if I put them together, this guy, this left hand side, okay, this is left hand side over here. Okay, so I have y tilde double dot t plus y tilde t squared, which is t squared, because 0 plus t equals t squared, which is equal to u tilde t squared, because u tilde t is t, so this should be t, u tilde t is t squared. Okay, which means, yeah, that's true. And also I didn't verify the satisfying initial conditions, right? So y tilde t at t0, so is t1, t0 is 0. Yes, it is true. And also y tilde t dot at t0 is 1, because this is always 1. Right? The derivative is always 1. Okay, so yeah, it satisfies all the conditions over here. So what we can see here is I can see x tilde. If I put x tilde, it's just y tilde and y tilde dot, right? Because the x is given by x1, x2, which is y and y dot. Okay, so x tilde will be just y tilde and y tilde dot. Y tilde is t, right, up here, right? Y tilde is t. Y tilde dot, you take a derivative of this guy. It's just with respect to t. So dt over the derivative t over t is 1. That's why this x is this. Okay, of course you can say y tilde is t, which you already know that. Okay, so I have a nominal. This is my nominal x tilde, this is my y tilde. I already figured out. Okay, now I complete step 1. For step 2, I just need to do the partial derivative. So step 2 is a sub t is partial f over partial x. What it's trying to do, as I mentioned, is partial f. So if I do this over here, so remember, I sort of can consider this is my f, this is my f, this is my g function, right? Because this is my f, you can consider f has 2. If I copy this f over here, so this I copy the f over here. So we sort of have 2 functions for the f, the f1, f2. f1 x ut, just x2. Okay, so this function is given by x2. f2 x ut is the function given by u minus x1t, x1 squared. Okay, that's what I have the 2 functions. So what I do when you have this one, this a is you do partial f1, partial x1, partial f1, partial x2. So on and so forth. That's what you do first row. First row is always a partial of the first function you have over partial x1 until you partial f1 over partial the last state. Okay, that's the general form. Okay, first row. You can do the same. The second row will be partial f1 over partial x2. Sorry, it should be partial f2 partial x1 and so on and so forth. Partial f2 partial x and so on and so forth. That's the principle. You do that. So here I have only 2 functions. Of course, I only have 2 states, x1, x2. So I have to partial f1 x ut over partial x1. Sorry, partial f1 x ut over partial x1. Partial f1 x ut over partial x2. That's the first row. The second row will be partial f2 x ut over partial x1. Partial f2 x ut over partial x2. Of course, don't forget about to evaluate the entire 4 values of the matrix at the value when x is equal to x tilde and y is equal to u tilde. Okay? So if I do the partial derivative, so the first one for f1, okay, f1 is just the function itself just given by x2, right? So partial f1 over partial x1, because this guy is x2, so partial x2 over partial x1 is 0, yeah? And the partial f1 over partial x2, because partial f1 is x2, partial x2 over x is 1, that's why it's 1, okay? So this guy is partial f2 over partial x1, so f2 is u minus x1 squared. So you partial this guy over partial x1, okay? So because u is not function x1, so this is gone. And partial negative x1 squared is negative 2x1, okay? So this guy partial x2, if you do partial x2, for example, the second one, so you get 0, okay? That's why it's 0, 1, negative x2, x1, and 0. Evaluate x tilde, y is y tilde, okay? So now we basically have to replace all x by its tilde. For example, here x1, I have to replace x1 by its tilde. This guy should be replaced by x1 tilde because I have to replace every x by its tilde. It's nominal state, right? So what is x1 tilde? X1 tilde is y. X1 tilde is, if I look at it here, x1 tilde is, if you do tilde, you also have tilde, right? X1 tilde is y tilde. Y tilde is, if I look, y tilde here, I don't confuse t, okay? So here I just replace x1 tilde is y tilde, which is t, right over here. So it's negative 2t, 0. So here you only have t, you shouldn't have any x tilde, x inside here. This one must only have t or a number. It does not involve anything like x tilde or x, should not get involved. Okay, similarly for bt, so bt is you do partial f1 over partial u, so the row will be partial f1, partial u. You can also have multiple u if you do partial f2, partial f1, partial u2, you do the same thing. So also for partial f1 over partial u, and if you have let's see. And you do similarly do partial f2, partial u1. If you have multiple input, you do the same row, and until you do partial fn over partial u1, so on and so forth. You do the same principle. Because here I only have one input u, so I just have partial f1 over partial u and partial f2 over partial u. Okay, so f1 is again is x2, so partial u will be 0, and partial f2 over partial u, because this is u minus x1 tilde, x1 squared. You partial this guy over partial u, it just gives us 1. Okay? Ct will be just partial g over partial x1, partial g over partial x2. So this is, you see, is a little bit different from the, C will be a little different from the previous one. So C typically is given by this. It's partial g, is a transpose that partial g1 over partial x1, partial g1 over partial x2, so on and so forth. This is partial g2 over partial x1 and partial g2 over partial x2, so on and so forth. Okay, let me check. That should be okay. Oh, that's also the same principle, I guess. Okay, this is a partial g1 over partial x2, so on and so forth. This is partial g2 over partial x1, so on and so forth. Yeah. So this ct will be partial g over partial x1 and partial g over partial x2. And of course here I forgot about to put it here. Should be evaluated at x is x tilde. And u is u tilde. So apparently here I don't have to care about that because it's constant, doesn't matter which nominal value we have. This is x equal to x tilde and u is u tilde. Okay, again if you do the g is just given by x. Let's say g, what is g here? My g is just given by x1. Okay, so you do partial g over partial x1, yes, because 1. Partial g over x2 is just 0, so it's 1, 0. So d will be partial g over partial u. Okay, you can follow the same principle to figure out what is the dt. Apparently g is not a function of u, so the partial of that will be 0. So if you do that, you can, the last step is to define x delta, which is xt minus x tilde t, which is you replace what the nominal solution we figured out for the x, which is t and 1, and y delta is yt minus y tilde t, which is yt minus t. This is my nominal output. U delta will be ut minus utility. Utility is t squared, right? So once you define that, you can say the linear system is given by x delta dot is 0, 1, negative 2t0, x delta plus 0, 1, u delta. Y delta is 1, 0, and x delta plus 0 times u delta. So basically here, which have here, this is A is t, so this is B. Of course, you can say B sub t, this is C sub t. This is d of t, right? So here you might have found when you do this one, you must have the a and b and the cd. They are not a constant. They dependent on the actual t value. But a t and b t and c t and d t, they are not a function of x tilde t. Not a function of xt, not a function of yt, anything like that shouldn't appear here, okay? So you don't have ut, you also don't have ut inside. So it's not a function of any of this, okay? It should be a function just for t or some constant value.